Welcome to RFIC design class. This is your lecture 12, unit 2. So we are discussing about transceiver architectures, and in the previous class we discussed about Hartley architecture, Hartley receiver, where we discussed some of the drawbacks. And if you look at one of the main drawback with Hartley architecture is uh, we know that in the Hartley architecture, it uses a 90-degree phase shift operation in order to cancel the images, and that is implemented using an RCCR network. So when we analyzed the variations in the absolute values of R1 and C1, we understood that there will be definitely mismatch in the gain uh, for this RCCR network, and that may result in imperfect cancellation of images. So that is one of the main drawback of Hartley, and in order to eliminate that specific drawback of the issues with RCCR network, we are looking at another architecture which is called as Weaver architecture. This is also an image reject receiver architecture, where the 90-degree phase shift operation is replaced using one more quadrature mixing. That is what we have seen yesterday, and this is the architecture of Weaver. Now we haven't written the equation, so what we'll do, we'll analyze this both mathematically and graphically. So for mathematical analysis, we are supposed to look at the signal and the image components at various points in the architecture. So we have to write the signal and image at points A, B, C, and D, and then after filtering at E and F, and we have to see how the intermediate frequency can be generated by cancelling images and by adding the signal component. So we'll start our class by writing the components at A, B, C, D, E, and F, and then we'll write the intermediate frequency component. Yeah, yesterday we stopped at this point where we have the signal, which is x of t, which is having a signal component and an image component. That is x of t. Now, if you look at point A is signal, the x of t component, which is multiplied by cos omega 1 t, then it is low pass filtered. So that means the higher frequencies should be filtered. So when I write A, it will be x of t multiplied by cos omega 1 t, removing the high frequency component. So I can directly write what is xa of t. I hope some of you would have tried this. So it is xa of t is a signal by 2 cos omega c minus omega 1 into t. That is so there is this the phase shift components, as of now I'm neglecting. When you write a signal, generally we write in the form of cos omega ct plus a small phase shift of phi. So for these operations, I'm just neglecting. We can write it also. That is not a problem. Just for simplicity, I'm just neglecting that. Now, multiplying with cos omega 1t will give you two components, one at omega c minus omega 1 and another one at omega c plus omega 1. So this component, since it is after low pass filtering, I am retaining only the low frequency component. This is a signal component. Similarly, we'll have image component, which is a im by 2 cos of omega im minus omega 1 into t. Right, this is the image component at xa of t. Similarly, x of t, when it is multiplied by sine omega 1 of t, you will get xb of t. So that will be minus a signal by 2 sine of omega c minus omega 1 into t minus a image by 2 into sine of omega image minus omega 1 into t. This is your xa of t and xb of t. So looking at the architecture, we have now written the components at xb and xa of t and xb of t. That is after low pass filtering. Now what we should do is we have to again multiply those components, or again quadrature mixing should be done. So mathematically the components at xa of t and xb of t should be multiplied by cos omega 2t and sin omega 2t. So when I do that, I'll get xc of t, which is xa of t multiplied by cos omega 1t, sorry, cos omega 2t. So when I write that, which will be equal to, so xa of t is having, there are two frequencies, omega c minus omega 1 and omega im minus omega 1. Now I am multiplying with cos omega 2t and I am writing the components before filtering. So the points which is marked as c and d are before filtering. So why am I writing these points is just to analyze the higher frequencies there. So understand what is a higher frequency and then we'll eliminate those components, and there we will write the components at E and F, right? So are you guys with me? Can I get some response in the chat box? Are you guys with me? All right, okay. Yeah. Now let me write what is xc of t. So xc of t can be written as a xa of t. So this a signal by 2. Again, there will be one more 1 by 2. So this is a signal by 4 cos of omega c minus omega 1 minus omega 2 uh, plus image component by 4 cos of omega 1 minus omega 2 into t, right. So these are the difference component. Similarly, there are two components which can be written as a signal by 4 cos of omega c minus omega 1 plus omega 2 into t plus a image by 4 cos of omega im minus omega 1 plus omega 2 into t, right. So this is xc of t. By writing the components at xc of t is by xa of t multiplied by cos omega 2t. Similarly, I'll write at xd of t also. So xd of t, which is xb of t is multiplied by sin omega 2t. So when I do that, I'll again get 4 components. Since it is sin omega 2t, I'll write with this minus cos of omega c minus omega 1 minus omega 2 minus image by 4 cos of omega im minus omega 1 minus omega 2 into t plus I'll get the sum components a signal by 4 cos of omega c minus omega 1 plus omega 2 into t, and plus the last component is a image by 4 cos of omega im minus omega 1 plus omega 2 into t. So these are the components at xc of t and xd of t, right. Now the important point here is, if you look at the architecture, we know that whatever we have done now is the frequency point at the components at point c and d, and there we have two sets of components for signal and image. One is sum and one is difference. Now we have to identify the higher frequencies in that, and we should eliminate the higher frequency components. Now can you guys tell me which all frequencies to be eliminated from this xc of t and xd of t? You can unmute and speak, one of you. From xc of t and xd of t, which are the components we need to remove by identifying the higher frequencies? Hello, any response? Please unmute and speak because I'm not looking at the chat box right now.
Last two from XC.
Last two in the sense, so in XC of T are telling this should be removed and this should be removed.
Yes, sir.
Okay, and similarly in XD, the last two.
Yes, sir.
Oh, that means these two. All right, so let us verify whether the components which I marked in red are high frequency components or low frequency components, right? So let us just verify that. So in order to verify whether those components are high frequency or low frequency, let me verify the mixers. We know that there are two set of mixers in each arm, right? And for both mixers, I am considering LSI. So LSI is considered for both the mixers. So let us understand each mixer. So the first mixer, say this is the first mixer. To the first mixer, we have the input component. Input component, I am marking it as omega C as the RF input, or the desired signal is omega C. Now the other input is actually omega 1, that is a local oscillator signal. Right. So since it is LSI for mixer, what I'm making sure is omega C is greater than omega 1. That is a condition. Now, if that is a condition, if I mark it, uh, say this is the desired signal which is at omega C, and since it is low side injection, I am marking omega 1 here, which is the local oscillator frequency. Similar, now we have to look at image position also. So now since it is LSI, we'll have image here at a specific frequency, and I mark that frequency as omega IM, right? So I'll mark this frequency as omega IM. This is the scenario for the first mixer, right? Now I know that omega C is greater than omega 1. Also omega image is less than omega 1. These two things are straightforward from the location of the signals in the spectrum. We can directly say this, right? All right, so let this be here. Now we have one more mixer. Now we have a second mixer. So second mixer also have two components. One input is a signal at omega 2, and another input is, so can you tell me what is the input signal for the second mixer? What is that frequency?
Omega C minus omega 1.
Yes, omega C minus omega 1 is actually the desired input signal to the second mixer, right? With omega 2 as the local oscillator signal. Now, when I look at the spectrum of this mixer output, so what we have now is after down conversion. So if I look at the output of first mixer, definitely images. Image also will be there, right? Because we haven't done any image rejection filter, or we haven't used any image rejection techniques. So at the input of second mixer, what I have is a component, a signal component, which is at omega C minus omega 1. Probably I'll mark it as this is a desired signal. On that, upon that, I have the image also, right? So this is omega C minus omega 1, and if you look at the image frequency, I can write that as omega 1 minus omega IM, right? Both are omega C minus omega 1 and omega 1 minus omega IM. Will be both are same, and both will be down converted into a single intermediate frequency. That is why we call this as intermediate frequency. This is actually our intermediate frequency, omega IF. I hope this is clear. But one thing to note here is omega C minus omega 1 and omega 1 minus omega IM both are equal, right? Now this is the input, or this is the desired signal and the image which is appearing at this point, this location, right? Now again here for the second mixer, it is low side injection. Since it is low side injection, I have to mark the second frequency towards left side, which is omega 2. Since it is low side injection, omega 2 is actually on the left side of the signal. Right. Now, so why I have started this discussion is to identify from this xc of t and xd of t, I need to identify which are the which are the high frequency components that will be eliminated by the low pass filter, right. So to do that, what I am writing here is, so from this by looking at this spectrum, I can clearly say that omega 1 minus omega im, right, that is the intermediate frequency, that is definitely greater than omega 2, because omega 2 is a local oscillator and we are actually going for low side induction. Similarly, omega c minus omega 1, omega c minus omega 1 is also greater than omega c minus omega 1 is also greater than omega 2, right. 1 second. All right, so omega c minus omega 1, yeah, so this is also greater than omega 2. Uh, now what I can write here is omega 1 minus omega im. Okay, so now with this understanding, can you tell me which all components can be removed, or which are the high frequency components here? Got an idea? Because we know that omega c minus omega 1 is actually greater than omega 2, or omega 1 minus omega im is also greater than omega 2. Now the low frequency component should be either omega 1 minus omega im minus omega 2. That means this component is definitely greater than omega 1 minus omega im minus omega 2. That is one understanding. And the second thing is, if omega 1 minus omega im plus omega 2 is greater than omega 1 minus omega im minus omega 2, then I can also write omega c minus omega 1 plus omega 2 is actually greater than omega c minus omega 1 minus omega 2, right. So if that is the case, if this is the case, these two components will be retained, right. So I will write here, this will be filtered and this will be retained, right. So now can you look at the previous equation and tell me which all components will be eliminated? So we thought these two, right, directly looking at the components, we thought these two will be eliminated, but actually the component which is getting eliminated is one is this, because this is omega im minus omega 1 minus omega 2, that is the component which will be eliminated by our analysis just now, and other, yeah, this will be definitely eliminated. Similarly, on the second component, this will be eliminated and this will be eliminated, right. I hope this is clear. A simple analysis I have done by looking at the frequency components coming to both the mixer. I have just analyzed the components which will be retained and components which will be eliminated or filtered. So this will be retained and this will be filtered. So if that is the case, I can directly write from C and D, those components will be eliminated, and I can write what is x e of t and x f of t. Right. So what is x e of t? X e of t is a signal by 4 cos of omega c minus omega 1 minus omega 2 into t plus a image by 4 cos of omega im minus omega 1 plus omega 2 into t. So this is x e of t. Similarly, x f of t can be written as when you write x f of t, we have to eliminate these two components, right? So x f of t is minus a signal by 4 cos of omega c minus omega 1 minus omega 2 into t plus a image by 4 cos of omega im minus omega 1 plus omega 2 into t. Right. Is this clear? Can I get few response in the chat box? I can see chat box now. So all right. I hope you are following, right? Okay. Now, if this is xc of t and xf of t, in yesterday's discussion, when I have yeah, so in this block diagram of Weaver architecture, I told that this we will decide by looking at the components of x e of t and x of t, whether this should be combined or subtracted. Now, can you tell me what should be done? X e of t and x f of t, should it be added or subtracted by looking at these components? In order to get IF out, intermediate frequency, where we can, yes, it should be subtracted, because then only you can eliminate the image component. So what we should do is x e of t should be subtracted, x f of t should be subtracted from x e of t. That means I have to make a small change in the architecture. This should be minus. So when I do that, the final answer will be equal to, so these two components will be added. So when these two are getting added, it will be a signal by 2 into cos of omega c minus omega 1 minus omega 2 into t plus the initial phase difference, the phase difference what I have wrote also I have included now. This is the intermediate frequency IF out. All right. So the only difference is between Weaver and Hartley is we have used one more set of quadrature mixing, thereby eliminated the 90-degree phase shift operation which is possible through the RCCR network, and thereby eliminating the drawbacks of that RCCR network, right? So in this way you can cancel the images. Now the same thing you can actually do graphically also. Let me do the graphical analysis also here. So Hartley, we have the components on real and imaginary axis, but here since it is not there, this is comparatively easy to understand. We do not have any imaginary components here, right? So this is okay. Anyway, we'll draw in that form only. This is imaginary. This is the frequency, and this is the real axis. Yeah, I'm looking at your responses. Yeah, most of you have written it as E minus F. We need to subtract it, right? So one thing to be careful about Weaver architecture is the frequency components. At what all frequencies the components are coming, since we have a second round of mixing operation happening. So I'll write signal on here. It is omega c minus omega 1 minus omega 2, which is the signal component, and the other side it is minus of omega c minus omega 1 minus omega 2. So this is the signal component which is having real amplitude, so I'll write this as signal component. This is x e of omega. So what I have written now is x e of omega. So we can actually do graphical analysis by plotting it for all the points, but anyway, that doesn't matter here. This is x e of f, and if I draw for x f of omega, there also the components are same, omega c minus omega 1 minus omega 2, and minus of omega c minus omega 1 minus omega 2, and we have components which is having the amplitude is negative, right? So these are the values that we have seen even from the equation. X f of t component is having a negative amplitude, so it is opposite. Now what we need to do is we need to subtract it so that we can retain the signal component. Similar way, if I draw for image, if I draw for image here, this is imaginary axis, this is real and omega. Now when I look at the image frequencies, so let me mark it in terms of the same thing. It is omega c minus omega 1 minus omega 2, which is a signal component. But we know that omega c minus omega 1 is the desired signal, and at that point you will get an signal image signal which is at omega 1 minus omega m. Both are same, minus omega 2. These two are equal. So on the other side also I can write it as minus omega c minus omega 1 minus omega 2, and these are the interferers or the image signals. Same thing happens even for x f of omega. There also it is omega c minus omega 1 minus omega 2. Here also it is minus of omega c minus omega 1 minus omega 2, where we have equal signal components. So in order to cancel the images, we have to subtract it. So this is x e of omega and this is x f of omega, where these are the image components. So what we need to do is we have the final combiner where these two components, I think from top it is f is coming, so this is minus and this is plus. So that will give you if out. I hope this is clear. Are there any doubts on this? Any doubts? So looking back at the architecture, yeah. So this is the architecture, and we have analyzed both analytically and graphically. Now, okay. So if you have doubts, we can discuss. Now, one question. Since I am using two sets of mixers, I think somebody has pointed out this before also when we have. I think when we discussed about dual down conversion receiver, this discussion point has come in. So the first mixer will have some image. Now you have a second mixer also. So are you seeing any other problem with respect to this Weaver architecture, since we have two sets of down conversion or two sets of mixing? One more image, yes, secondary image, that is true, yes. Yeah, so that is one thing we need to understand in this Weaver architecture, that is a problem of secondary image, right? So let us see what is a secondary image. So to understand about secondary image, so to understand about secondary image, we'll try to understand that graphically with a spectrum, and also by taking some examples which can cause secondary images, right? So let me. So what I'll do now is I'll consider the RF input. Along with RF input, I'll see the IF output at the first mixer and the second mixer, right? So this is actually to represent our RF input, right? So when I represent RF input, let me mark this as the input signal. You can call this as omega in or omega C, both are same. Just to show that it is RF input, I am using the notation as omega in, right? Now for omega in, we know that when it comes to the first mixer, it is LSI for the signal. So mixer frequency omega 1 was on the left side, right? Now let me mark this this component here. What I have is the first LO signal, and this is the desired signal. This is desired signal, and this is the first LO component. Now now I am considering a component which is okay. Let it be there. So this is your desired signal. Now let us look at the first IF output. So first IF, when I say it is first IF, definitely it will be shifted to a lower frequency. So that I'll show in this graph also. Omega in is at a higher frequency, but now we have a signal which is at omega omega in minus omega 1. So let me mark somewhere down here. So what I'm drawing here is first IF output. So for the first IF is at omega omega in minus omega 1. This is the point where we have the first IF. This is the first IF. Now for the second mixer, second quadrature mixing, we have, all right, I was using this color. Omega in minus omega 1, and for the second LO frequency is at somewhere this point, so at omega 2. So let me mark this as second LO, which is smaller than omega in minus omega 1, right? Now now if I look at the output of the second mixer, that is after the yeah, again it will be down converted, it will be to a somewhat lower frequency. If I draw that here, what will be that frequency? Can you tell me what is the second IF output? Can I get response in chat box? Second IF output, it is omega in minus omega 1 minus omega 2. Very good. Yes. So there you will get the yeah, this is your second IF output, omega in minus omega 1 minus omega 2, right? Now we are trying to look at a component called as secondary image. So in order to understand this secondary image, what I am doing now is, so anyway we analyze the first image, right? So now we have three frequencies. One is omega in, which is the input frequency. Second one is omega 1, which is the first LO, and third one is omega 2, which is the second LO frequency, right? Now okay, now I am considering a frequency. I am assuming that whenever an RF input is gone, we know that it will be a band. Now I am looking at a frequency somewhere which is somewhere in between this omega in and omega 1, right? If I have a component here which is having a frequency lesser than omega in and greater than omega 1, and I'm marking this frequency as, let me mark this as 2 omega 2 minus omega in plus 2 omega 1. This is what the frequency I am taking. Why I have written in this form is this frequency is actually obtained by understanding what is a secondary image component, right? So for the time being, assume that there is a frequency component which is having a value between omega 1 and omega in, right? And that specific value I have taken as 2 omega 2 minus omega in plus 2 omega. We will come back to this little later. Now, when I look for the yeah, so when yeah, any questions? All right. Now, for the first IF output, I have shifted omega into omega in minus omega 1. Right, and there is a second LO component at omega 2. Now, what will happen to this frequency? If there is a frequency component which is lesser than omega in, at the first IF, what will be the frequency of this? Where this pink component will get shifted? Any idea? Since the first mixer, this component will be mixed with omega 1, right? So what will be okay, yeah, you will get sum and difference component, but since there is a low pass filter, I am looking actually for a difference component. Yes, so it will be we will have another component here. Let me mark it as 2 omega 2 minus omega in minus omega 1, right? I hope that is clear. It is 2 omega 1 here, and when I shift that, sorry, it is plus omega 1. When it is mixed using omega 1, the difference component will be 2 omega 2 minus omega in plus omega 1, right? Now, can you tell me what is this 2 omega 2 minus omega in plus omega 1? Two omega 2 minus omega in plus omega 1. Yeah, first image, okay. Yeah, so if you look at this, how will I write the image component at the first stage? Image component can be written as 2 omega LO minus omega in. This is one way to represent image, right? I'm writing actually the image component at the first IF output. So what is 2 omega LO? 2 into omega LO is omega 2 minus omega in is, which is omega in minus omega 1, right? So that is 2 omega 2 minus omega in plus omega 1. What I have plotted here is actually the first image, right? Now, what will happen at the second IF output? Yeah, it is a, yeah, this is the image for omega in minus omega 1, very true. Now, what will happen for second IF output? At second IF output, this omega in minus omega 1 will be shifted to minus omega 2 to this point. What about this? This also will be mixed, and this also will be shifted to the same point, right? So we can see that one image will be falling actually here. What is this frequency? This will be omega, yeah, it is omega in minus omega 1 minus omega 2. So this is actually your secondary image. And this is very much possible that a secondary image will occur at the second IF output. The reason is we are using two mixers and we have all the signal component between omega 1 and omega in also coming in. So if you substitute some numbers to omega 1, omega 2 and omega in, we will get to know that these frequencies will actually fall in place, right? So now the question is, since omega in minus omega 1 minus omega 2 is secondary image, Beaver architecture is anyway not cancelling secondary image. Beaver architecture, with the discussion what we have done till now, we understand that primary image or the first image will be definitely cancelled out. Now, what will happen to this secondary image, or how can I get rid of this secondary image? All right. I'm not able to see the chat box. Okay, so I'll just conclude this. So what happens here is the first image will be definitely cancelled by the first images will be definitely cancelled by uh, the Weaver architecture. But now since we have a secondary image which is falling exactly on the signal, one possibility is if we try to make, yeah, one possible solution is if we try to make the second IF, the secondary IF equal to 0, we can actually eliminate this. How is that possible? How can I make second IF equal to 0? Making second IF equals, second IF frequency is omega in minus omega 1 minus omega 2. When I say this should be equal to 0, the meaning is the omega 2 value should be equal to omega in minus omega 1. That means if I am introducing a if the second mixer is having a local oscillator whose value is equal to omega in minus omega 1, omega in minus omega 1, then mixing of that local oscillator and the first IF output will definitely this will be directly going to the baseband, right? Since these two are equal, this will be directly going to the baseband, and then thereby we can actually eliminate the image component there. All right, I hope that is clear. So what we have discussed now is we have RF input and there are two stages, first IF and second IF stage. We consider a signal which is lying less than omega in, and that led to a frequency or a frequency which is actually corrupting the signal at the second IF output, and that we called as secondary image. And one possible solution to eliminate the secondary image is actually by making the secondary IF value equal to 0, that is by using a second LO frequency as omega in minus omega 1, right? So this is about secondary image in Weaver architecture. So what we will do is we will continue in the next class with the next type of receiver. Now I can actually take questions.